Question number 6. An air source heat pump transfers energy from the air outside a building to increase the temperature of the air inside the building. Figure number 13 shows an air source heat pump. So this is a heat pump. It consists of two parts. If you look here, one is inside the building and other is outside the building. This is the condenser and the liquid coolant is present inside. When this liquid coolant it goes from inside of the building to outside the building, it converts into the vapors and vapors start moving here towards the compressor. From the compressor, the air is moved inside the building and the heat is given to the surrounding air inside the building, which helps to increase the temperature of the building. The compressor is connected to the main electric supply. We can see here, this is the compressor which is connected to the main electric supply, and this is an important point and we need it for next coming questions. The pipe in the heat pump contains a substance called coolant. So we can see that the coolant is present, which is moved inside the pipe. In the evaporator, in this part of the heat pump, energy is transferred from the air outside the building to the liquid coolant. The surrounding air particles have energy and they give the energy to the liquid coolant and the liquid coolant converts into vapors. The temperature of the coolant increases and it evaporates. So this is the key information that this liquid coolant it converts into the vapors and become more energetic as compared to the liquid form. 6.1 is an A1 question and this question is from the topic of internal energy. Explain what happens to the internal energy of the coolant as its temperature increases. As the temperature of the coolant increases, it means that the distance between the particles it increases. The particles have more kinetic energy and more potential energy. As the result of that, we will say the internal energy of the coolant increases. Let's see the model answer. As the temperature of the coolant increases, the kinetic energy and the potential energy of the particles it also increases. Means the internal energy, which is actually sum of both kinetic energy and the potential energy of the coolant, it increases. 6.2 is an AO1 question and this question is from the topic of specific latent heat. What name is given to the energy needed to change the state of the liquid coolant? The question is we need energy that is required to change the state only. So it means the energy is used to change the state, not to increase the temperature. So the name of the energy which is used to change the state is called latent heat of vaporization, or the student can write only the latent heat. Latent heat of vaporization. 6.3 is an A1 question. What happens to the mass of the coolant as it evaporates and becomes a vapor? We know that the coolant is moving from the liquid state to the gas state. It means that the total mass of the coolant within the heating pump always remains same. It just changes the state from liquid state to gaseous form, but the total mass of the coolant it always remains same. So the mass of the coolant stays the same. 6.4, again it is an AO1 question. It is a knowledge based question. The compressor increases the density and the temperature of the coolant vapor inside the pipe. Explain why the pressure in the pipe increases. So the key information is given here. The density will increase and the temperature will increase. Density means there are more particles at a point. And this question is from the particle motion in the gases. We need to use figure number 13. In figure number 13, the compressor, it compresses the particles closer to each other. Therefore, the density in this area will going to increase. It's not only the density, it is also the vapors which have the high energy. They are also compressed by the compressor. So in this region, there are more particles with high temperature. As the temperature of the coolant particle is increased, it means there is more collision between the particles in this region. Also, there are more particles because it is already mentioned the compressor is compressing the vapors, and there are more vapors, more particles, and they have the high energy. Therefore, there are more frequent collisions between the particles, and they can easily lose energy into the building. Let's see the model answer. As the temperature of the coolant vapor is increased, means the particles have high internal energy. Therefore, there are more collisions per second between the particles. Also, the particles will apply greater force per collision inside the compressor walls, which increases the pressure on the walls of the compressor. 6.5 is an AO2 question. It is an application based question. The student need to use the given information here, and they need to calculate the specific heat capacity of the air. The key information is given here. The condenser transfers energy from the coolant to the air in the building. When the total energy input to the heat pump system is 1560 kilojoules, the temperature of the air in the building increases from 11.6 degree to 22.1 degree. The efficiency of the heat pump system is 87.5 degree. The mass of the air inside the building is 125 kilogram. Calculate the specific heat capacity of the air in the building. Give your answer in standard form. This question is from the topic of efficiency, specific heat capacity, and energy change. We know that the mass of the air is given. The change of temperature is already given here. We can find easily two different temperatures. And with the help of that, we can find the change in temperature 22.1 degree minus 11.6 degree. And the energy given to the heat pump, that is also mentioned. But the key information is given here. This is energy given to the heat pump, but the pump is only efficient 87.5% only. Therefore, first of all, we need to find the temperature difference for specific heat capacity. Second, we need to find the energy which is given by the pump, that is 87.5% of the energy given, that is input energy. Then we can find the energy. With the help of that energy, we are going to find the specific heat capacity. Let's see the model answer. From the given data, we have the mass of the air, that is 125 kilogram. The efficiency of the pump is 87.5% of the input value. We convert it from percentage into number form, that is 0.875. We need to find the change in temperature, that is delta theta. Initial temperature is 11.6 degree and it changes to 21.1 degree. So the change in temperature is 10.5 degrees Celsius. Student will get 1 mark for finding this temperature. The total energy input is 1560 kilojoules. We convert it into joules because the unit is kilojoules here. You need to find the energy transfer into the building, which is output energy or the work done by the pump. First of all, we need to find the work done by the pump. It is already given in the question, that is 87.5% of the energy input. We found the energy, that is actually the 0.875 times the input energy, and we got the energy given by the pump or the output energy. So we know that energy is equal to mc delta theta. This is energy which is used by the heat pump. So we are not using the energy input, total energy input. We are going to use the energy or the work done by the pump. So the energy is equal to mc delta theta, specific heat capacity formula. Energy is given here. Mass is already mentioned, 125. We need to find specific heat capacity, C value, where the change in temperature is 10.5 degrees Celsius. To make C as a subject, this value will go on the other side and divide our energy. Answer is 1040. The demand of the question is the answer must be in standard form. Standard form means in the power of 10. So decimal will move 3 digits on the left, and we have 1.04 10 raised power 3 joules per kilogram Celsius. The answer is 1.04 10 raised power 3 joules per kilogram Celsius. 6.6 is a combination of AO1, AO2 and AO3 question, and this question is from the topic of efficiency. The air in the building gains 400 joules for every 100 joules of energy transferred from the main electric supply to the compressor. An advertisement claims that the heat pump system has an efficiency of 400%. Explain why the advertisement is not correct. If you see here, the output energy is much higher than the input energy. The efficiency cannot be higher than the 100%. And on the other hand, it is not mentioned that in the figure number 13, the energy is also coming from the air outside the building. If you look here, when the coolant is moving, the air particles from the outside, they give the energy, and the liquid coolant changes into the vapors. Let's see the model answer. The total energy input, which is 400 joules to the air inside the building, is much greater than the energy input 100 joules to the compressor from the main electric supply. The efficiency must be less than 100%. If you look here, the output is 400 and input is 100 joules, so this efficiency is more than 100%, which is not possible. This shows that the advertisement has ignored the energy input from the surrounding air outside the building. The air present outside the building, they give the energy to the liquid coolant, and the liquid coolant converts into the vapors. They take the energy from the air particles and they convert into the vapors form. So the advertisement ignored that information and mentioned that efficiency of the pump is 400%.